So we've been talking about ionization energies, and we saw that there were some trends in ionization energies. Let's review. Let's go back. We see that there are trends that as you go across a period, ionization energy increases. That means it's harder to remove an electron from an atom over on the right side of the periodic table. As you go down a group in the periodic table, we see that it becomes easier to remove. But there are some exceptions to this. If we look between groups 2A and 3A, we would expect that boron has a higher ionization energy than beryllium, but it's actually smaller. And the reason for this is that boron is losing a 2p electron, whereas beryllium is losing a 2s. So let's look at the orbital diagrams for boron and beryllium. So boron has 3 valence electrons. So there are 2 in the 2s, and then there's 1 valence electron in the 2p. And for beryllium just has 2 valence electrons, and its 2p sublevel is empty. So if we're going to ionize beryllium or boron, we're going to do so by removing an electron. For boron, we're removing this 2p electron. The 2p sublevel is a little bit higher in energy than the 2s sublevel, and so this electron is easier to remove than the 2s electron from beryllium. And so we see this exception in the trend. If we go back to the graph, we can see that very clearly. It's right here. So between the second and the third group, the trend is not followed. And we see that over here also, that this one is lower than that one, comparing the main groups. Any questions about that?
So from the previous lecture, the more dramatic changes side to side.
Yeah. Basically, what I want you to remember are the general trends. So I would not necessarily expect you to remember this exception, but I think it's important to learn about it and understand why it's there. Okay. There's another exception between groups 5A and 6A. And again, that has to do with the types of electrons that are being removed and what sort of a situation that they're in. So if we look at nitrogen, nitrogen has a half-full 2p sublevel. When these sublevels are completely full, half full, or completely empty, that is more stable than some other situation. For oxygen, the 2p sublevel has 4 electrons in it. So 2 of them are paired and 2 of them are not paired. So removing this paired electron is easier than removing one of these electrons from nitrogen. And so although the trend says that oxygen being to the right of nitrogen on the periodic table should have a higher ionization energy, because we're removing a paired electron to form a half-filled shell like nitrogen has, it's actually easier. And so again, we see that gap. If we, talk about the quantum hotel, in this 2p room, we've got 2 guys that have to share a bed, right? And so this guy who's having to share, he's a lot more willing to get kicked out of the room. These guys here are pretty comfortable. They each have their own bed, right? They're kind of happy with that situation. And so it's going to be easier to kick this guy out than to kick one of those guys out. Any questions? Now, what about a second ionization? So first ionization is removing 1 electron from an atom. The second ionization energy is how much energy is needed to remove a second electron. So you're removing 1 electron from a +1 ion. And we see that the second ionization energy is higher than the first, which makes sense because now you're taking that electron from a charged ion. It's already lost 1 electron. It's not going to be happy about losing a second electron. The other things that happen are that we have a higher Z effective, and the electrons that we're removing are a little closer to the nucleus now. Because when you remove an electron to form a cation, the cation is smaller than the original atom. So here is sodium and magnesium, and we're comparing the ionization energies. We see that the first ionization energy for magnesium is a little higher than for sodium, and that follows that trend. When we look at the second ionization energy for magnesium is roughly double that of its first. So that's okay. But then look at the difference here. For sodium, the second ionization energy is almost 10 times as much as the first. That's a huge change. The reason is that sodium has one valence electron. So when we remove the one valence electron, it takes 496 kilojoules per mole. After we've removed that, what does the sodium ion look like? It has 8 valence electrons. It looks like neon. It's got a noble gas electron configuration, which is particularly stable. If we're going to pull another electron off, we're going to mess that up. And so we see this huge jump. With magnesium, we don't get to that noble gas electron configuration until after the second ionization energy has passed. So we've ionized it twice, and now the third one is where you're going to be removing one of those core electrons, and that's where we see this huge jump. That makes sense? Here are some trends in the ionization energies, and so we're just going across that third period of the periodic table. And what we see here is this leap, the increase from 496 to 4560, from 1450 to 7730. And so we're showing here that this is removing the first core electron. And so that involves a large jump. And so we see this pattern going across the periodic table. Any questions?